So hello everyone, my name is Furmanek, and today we're going to talk a little about locks. I think it's my third time to Svitla, and it's always a pleasure to be here. So thank you for inviting me one more time. And let's carry on. Before we talk about locks, a couple words about me. I'm a software engineer for over a decade now, mostly working on currently on things related to machine learning, big data, text-to-speech generation, and that stuff. I'm also an author of a couple of technical books, one or two .NET, focusing on .NET, and one about maths and applied IOP. Feel free to take a look at my blog, drop me an email or line on Twitter, whatever works for you, if you had any questions after this presentation. And as it was already mentioned, feel free to type your questions in the chat. I will try to take them as we go. Okay, and let's begin. So the agenda for today's talk is we'll talk about locks. We'll learn some general concepts about locking, about critical sections, about primitives which we can use to lock the multi-threaded code. And then we'll go through some real life scenarios. So we'll see where those locks are, that they may be hidden or they may be even absent, and this will cause problems on our end. And we'll learn that they can be in any layer of the software engineering process. Then we'll go through a couple of algorithms, see some custom implementation, and that will be it for today. So general concepts, what are we going to talk today is we want to understand why locks are useful, how they are implemented, and what problems we may get with using them or with when we are not using them. But before we get into that, we'll need to actually understand what are we talking about. So the two common concepts in software engineering is concurrency and parallelism. And they are often like mixed with each other or understood incorrectly. So let's get some definitions before we move on so we know what we're talking about. So the concurrency is the ability to decompose an application into multiple parts. Like when we are talking about concurrency, typically we are talking about some resource, some access to a resource. So whether that's like a CPU, whether that's a file, whether that's some part of the code which only one thread should be executing, we are always talking about how those different threads can access that single resource. And however, the formal definition is that we can decompose the application into parts which can be executed out of order, meaning that when one thread wants to access the resource and then some other thread wants to do the same, those codes, those threads can be like interleaved, executed not in the order like which would be look similar in every single execution, or the order which would be intuitively deducted based on the source code. So generally, we want to get our application, cut it in parts, and then execute those parts in any order. When this is allowed, when this is possible, when this does not break the state, the application, the operating system, then we are talking that our application is concurrent, meaning that it runs correctly in the concurrent environment. Problems arise when the application does not work well, when we change the order of execution, change the order of the parts we are running. However, parallelism is something different. Parallelism is about executing multiple things at once. Those things may not necessarily be talking or be touching the same things, the same resources. If we are running two different threads which do completely unrelated, independent things, then we are executing them in parallel, but they are not concurrent in this sense that they are not touching the same resource. So we need to understand that concurrency is about accessing like the part which is on the border of two threads, which both threads want to touch. Parallelism is about the ability to run two things at the same time, literally at the same time. And it's worth noting that depending on what we are talking about, all those four scenarios are possible. So all the options, whether something is concurrent or non-concurrent, and parallel or not parallel, are possible. So we can have a code which is truly concurrent and truly parallel. So what we are talking about here is we have a code which, like when we have multiple CPU cores, this gives us the ability to run the code in parallel because each core may take a different thread. And also we can take the code which is concurrent, so it is allowed for the code to run in this out of order fashion. So we can cut it in parts and mix the order of those parts. We can take the same with concurrent and not parallel. And this is how the computers were used to work for many years. We had just one CPU core, but still we were running multiple applications and they seemed to work together at the same time, just like your operating system does, right? You do have your OS running and you do have multiple applications, your instant messenger, like document editor, web browser, whatever else, and they work in the way of context switching. So we cut those applications in parts and we execute every single part in like an out of order manner. And the resource we are talking about here, which is used concurrently, is the CPU. So every application tries to get an access to the CPU core, and the operating system decides how we are running those things, in which order and which application runs next. But we can also get a code which is not concurrent and not parallel. Okay, and this is batch processing. So early computers were operating in this way, meaning that when you started some application, the operating system could not stop its application, right? Could not evict it, could not stop it from running or take the CPU out of it, because this application was just taking the whole machine and running it, right? And this was a batch processing. There were some extensions to that, like we could have a supervisor tiny part of the application which could work in the extended mode, but those things generally are like single-threaded and nothing can stop them. This is not concurrent and not parallel. But we can also have something which is not concurrent and parallel at the same time. And what we are talking about here is, for instance, a bit level parallelism. So whenever we are talking about instructions which are running like the vectorized instructions, the way they work is they take multiple bytes of memory and perform the same operation on each of the bytes they are working on. So we can, for instance, take 4 32-bit integers and then add them or increase them in the parallel way, which is not concurrent, because every part is not running in this out of order way. So we can have any way, any option, whether something is parallel, not parallel, concurrent, not concurrent, we can mix those. And it's not that where something is concurrent, it must be parallel as well, or the other way around. It doesn't work this way. And being that said, the other important concept in terms of locking and accessing the memory and contacting between threads, etc., is how do we communicate? What do we share in between threads? When threads are actually trying to work in a concurrent fashion, we typically have the resource they want to use together. And that's why we need to have logs and all that stuff. However, now the question comes, what do we share between threads? And the one approach to doing that is the shared memory concept. So we have a physical memory, like in our random access memory in RAM unit, which is actually accessible by 2 threads, 2 applications, 2 processes, whatever. And exactly the same physical memory location is used by both of them. This is prone to multiple issues. We'll get to them a little later. However, that's generally the fastest way to communicate in between threads. Like shared memory is the fastest way. Even though we need to use logs, even though sometimes we need to use interlocked operations like compare and swap, but generally, this is the fastest way. However, it's not the only approach. The other one we can take is the message passing. So we can communicate between threads using some messages which are sent between one thread to the other. So we can think of any IPC communication and inter-process communication. We can think of sockets. We can even think of some like offline communication or communication which is greatly delayed. For instance, sending an email which is then processed automatically by the other operating application, right? And they can be used between multiple machines, something we cannot do with shared memory, that we cannot share we cannot share memory between threads running on multiple different machines, because typically there is not a single physical memory which would be accessible for both of them. Obviously, that changes depending on what the infrastructure structure look like? For instance, we may have like shared network storage, which technically we could say is a shared memory, right? Even though it's probably hosted on different machines, so we need to still to communicate with it like with message passing or RPC calls or whatever, but technically we are accessing the same resource, so we can think of that as being shared. However, the outcome, generally message passing, is slower. That is because we need to serialize the message, we need to send it over wire or any other communication channel, and then we need to deserialize it, parse it, interpret, and do all this stuff. Generally, it is slower when we are talking about inter-thread communication while running on the same machine. If we are running on multiple different machines, then obviously we cannot use shared memory. We need to go with message passing. And at the very bottom of the implementation, when those messages are received, there is some shared memory anyway. So we cannot get rid of shared memory altogether, but we can at least wrap it with multiple layers which provide us the message passing interface. Now, when it comes to shared memory, like locks are used because we physically have the same part of the memory, the same memory address, which we need to physically share between threads. And now what problems can occur? The most important problem, the most common one, is the lost write. Whenever you're doing the variable plus plus instruction, what you are doing under the hood is you read the value of the variable, you increase it in memory, so you do some calculation in your CPU registers, and then you write it back to the memory, right? And in between, when you are doing that, some other thread might have had read the memory, the same value you did, and then the other thread might try to be doing the same, like increasing the value, incrementing it, and then writing it back. Effectively, the write you do, so the value you tried to write or you actually did write the memory, is now gone because the other thread stepped in and overrode the value you stored in the memory. So that's the most important issue, the most common one. However, there are two others which are like bad as well. One of them is word tearing. So word tearing, technically, word tearing is like when we are trying to access a single element which is smaller than the smallest possible item we can access like in an atomic way. What am I talking about? Whenever we are working in the CPU, like in x86 architecture, typically the lowest unit, the smallest part of the memory we can read is like 1 octet, 1 byte, meaning 8 bits. If we want to modify a single bit of a particular octet, we cannot do that. What we need to do is we need to read those 8 bits, modify one of them in memory, like with bit mask operations, and then write those 8 bits back, write the whole octet back. And the problem with that, when we are dealing with this, is when multiple threads are trying to modify different bits of the same part of the same octet. They may be thinking that they are working on like different part of the memory because, hey, they are accessing different bits, but in fact, they are accessing exactly the same memory, which in turn leads to tearing the word like apart. So losing data and breaking the data, or even breaking the bits from some other part of the bit set. The other issue is atomicity. So when we want to write a big value, which we cannot write in one go, in one instruction. Imagine that now on x86 architecture, let's say that is like no matter whether 32 or 64-bit, we cannot write a structure which is greater than 128 bits. So we cannot write atomically something much bigger, like something bigger than that. If we try doing that without any locking primitives in place, then what happens is that we'll need to execute multiple writes in a series, okay? We'll need to write first lower 128 bits, then the upper 128 bits. The problem is that between those writes, we may be actually paused and like the context which may occur, and will be like the write will be stopped in the middle, and then some other thread may step in and try reading the whole value, and we'll get an inconsistent result. So what can we do about that? Those are problems which we need to solve in some way if we are to use shared memory like successfully. And the answer what we can do, how we can solve that, is we need to have a critical section. So the critical section is a primitive, like a code, which can be executed by one thread, one task, one execution unit at a time, meaning that when there is a block of code, if one thread starts executing it, then no other thread can start executing it until the first thread completes. This cannot be parallelized, meaning the critical section backed by the same critical, that's the same mutex or the same lock, cannot be executed in parallel. Only one thread can execute it. And there are a couple of rules of thumbs, what should happen or how we should implement critical sections. Well, they should finish in a finite time. This is super important because if you take a lock and then do something like an infinite loop, then probably it's not a good idea because you effectively have a deadlock in your application. Also, critical sections should be as small as possible, so you can finish them, execute them in shortest possible time, because otherwise you basically decrease the performance of the application. But now comes a very interesting question. What do we do, or what happens if there was a process executing a critical section and that process died in the middle of it? Imagine there are 10 instructions, and after executing 5th of them, the process dies because of an invalid memory access or because of any other issue. What can we do about that? Well, if we detect that such a thing happened, then we actually have a very tough question to answer. The question is, can we safely move forward or not? Can we continue or not? Because that thread was probably modifying some resource, which is now in a broken state, wasn't updated completely because half of the instructions were not executed. So this is something which we cannot solve just by using any locking primitives. This is a business decision, which we typically need to solve on a completely different level, be able to have enough logging to understand what happened, have a rollbacking mechanism, just like in SQL databases, or have some process which will tell us whether the data is broken or not, whether it's consistent or not. And there is a question on the chat. I have a question about Spinlock. Is it recommended to use it when switching contexts would cost more than just waiting for a few CPU cycles? How to measure this? What's the best approach to calculate? Is it worse or not? We'll be talking about Spinlocks later during this talk, so I'll answer that question a little later. So stay tuned. Going back to critical sections, so we do have a concept of a block of code which is executed by exactly one execution unit. Now comes the question, how do we guarantee that? And this is where mutex come to place. The the name comes from mutual exclusion problem. So we would like to have two threads and only one of them should be allowed to execute, so they should exclude each other mutually. And the thing is that mutex can be implemented in multiple ways. However, almost always, nearly always, it requires some atomic operation in a multiprocessor system. Because right now, nowadays, we are talking about multiprocessor systems. We do not have single processor systems anymore. And in that case, if we did have one, the way we could implement a mutex is just disabling interrupts. The interrupts are, if we are talking about computer, the computer has multiple physical devices, memory unit, drivers for, or physical devices like keyboard, like mouse, or maybe some CD-ROM, or maybe some printer, or whatever else. And those devices can come and notify CPU that, hey, something happened, and they want to get attention and execute some code. Like, for instance, there is a new network packet coming on the network card. So what those things do, they raise a signal on the bus, on a physical bus. So basically they turn on some switch and the CPU is interrupted. So they signal an interrupt and CPU tries to handle this interrupt. However, CPU can be configured to ignore those interrupts. In that case, the CPU will just continue executing the things like the application, the single-threaded application, and will not pause it to handle the signal know the interrupt from the network driver or whatever other thingy. So this is the way we could do that in single CPU computers. However, nowadays we are always talking about multiprocessors, and in that case, what we typically need to have to implement any locking mechanism, any locking primitive, no matter how basic, we always need to have some operations supported by the CPU, which allows us to atomically modify the memory in a test and set or compare and swap fashion. So the compare and swap, CAS for short, is the operation in which we are basically reading the memory, comparing it to some constant, and then setting the memory back with the value dependent on the result of comparison. So memory compared with some constant, if it's equal, then we modify the memory. Otherwise, we do not touch it. And this needs to happen automatically, so other CPUs, other CPU units cannot stop that. Other things are, where do we implement such a mutex? Whether we implement it in like a kernel mode or maybe in a user mode. Maybe it's provided by the operating system or by the libraries, or who can own the mutex, who can lock it, who can unlock it, who can take it recursively, whether there is reentrancy supported, multiple other things. So generally, mutex is a very basic concept once we start implementing that. However, if we want to have it like performing fast, if we want it to be like fair and to support multiple scenarios, then it's getting to be much harder than we may think. There are obviously different standardized implementations of mutexes. One of them is like WinAPI with create mutex, which is called mutant internally. In Linux, we have pthreads, so POSIX threads, which are typically implemented by the NPTL, so native POSIX thread library, because pthreads in Linux is just a standard of how we should implement the locking mechanisms. It's not an actual implementation, it's just a definition or the standard of this implementation. In .NET, we obviously have a class called Mutex, which gives us this behavior. Apart from Mutex, there are other primitives which we can use to implement the critical section, one of them being counting semaphore. So the counting semaphore, we could think of it as like a mutex, which allows us to count to some other number than just one. So it allows us to allow other multiple threads to enter the critical section, not only just one. Counting semaphores provide two operations, one of them being V, which is verhogen in Dutch, which stands for increment. So basically increment the value of the counter. And the other one is proberen, which is decrement from Dutch, which decreases the value of the semaphore. Now, the question is, and this is actually a pretty popular like interview question, what's the difference between a binary semaphore and a mutex? So binary semaphore is a semaphore which counts to one, so it allows only one thread to enter. So what's the difference between that and the mutex? And the answer is, if we need to understand or need to use those mutexes or those binary semaphores in more complex situations, we typically hit an issue with like reentrancy. So when we have a recursive function which calls a lock and tries to acquire a lock, mutex will typically allow us to take this mutex and carry on. So we can take it recursively, like 5 times from within the same thread. However, binary semaphore will not let us do that because binary semaphore has no notion of ownership. It's just a counter which can be increased or decreased. It doesn't track who increased the value and does not enforce things like that. Only the thread who decreased the value can increase it back. So binary semaphore does not support recursion because it doesn't track the owner. It doesn't notify when it's abandoned. It doesn't protect the thread owning the semaphore from termination because there is not a single owner of the semaphore. Like there is not a notion of an owner of a semaphore, right? Only mutex can be owned. So this is the difference between mutexes and binary semaphores and like counting semaphores in general. Again, we do have multiple different implementations in WinAPI, pthreads, or just .NET. And now we come to the question which was like to some extent asked on a chat. If we do have a spin lock, is it recommended to use it when switching context? Would it cost more? How should we use it, etc.? We come to a question like, if we want to take a lock, if we want to acquire a mutex, is it better to just sleep and get notified by the operating system when it's possible, allowed, when it can be acquired because it was released by some other thread, or should we do the spin wait? Should we like continue carry on in the loop? And the difference between those two approaches is that sleeping is generally expensive because it relies on the operating system. So we need to go to the kernel space, and it requires some kernel structures, requires context switching and multiple other things. So this is generally expensive. However, sleeping does not hog the thread, meaning that the thread is not like constantly running on CPU, consuming resources, or just generating heat doing nothing. However, the problem with sleeping is we can't use it in all circumstances. We can't use it in all the scenarios because it relies on the operating system. So if we are now implementing like a driver, like device driver, maybe sometimes it is possible that we won't be able to take the mutex with sleeping at all. On the other hand, spin wait, so basically circling in a loop, checking whether the mutex is available and taking it if it's possible, is called spin wait. So this can be done in all circumstances. However, it hogs the thread and the CPU. So basically we increase the CPU usage, generate tons of heat and use lots of energy, and we do not move forward. However, it is often used initially when we expect the critical section to be released soon. And now answering about part of this question. When to use it, and would it cost more for a few CPU cycles, or how long should we spin wait? The general rule of thumb is that we should spin wait for as long as the time of twice the time we expect the lock to be not available. So if we think that typically we should acquire the lock in like 4 milliseconds, because this is something we get from like performance load tests, whatever else, then we should spin wait for double the time, for 8 milliseconds. If we cannot acquire the lock after those 8 milliseconds, then we go to sleep. Okay. Now, obviously, the question is, where is the limit for how long should we spin wait? If we are taking the lock in like 5 seconds, should we spin for 10 seconds? The answer is nope. We should not spin wait for longer than like one quantum time, which is typically configured on our CPUs to be 15.6 milliseconds. So this is the longest time we should spin wait. Otherwise, we'll just be hogging the CPU. Obviously, those are rule of thumbs which strongly depend on the context we are talking about, the operating system, the application, the type of CPU, the type of device. We may not want to do that on like mobile devices. So generally your mileage may vary, right? But this is just a rule of thumb we should or we can consider. The other question we have in chat is, what do you think about barrier? Could you give me examples of when to use it? Well, when it comes to barrier, there are actually two different barriers I can think of. First barrier is a locking mechanism which tells us that, hey, this thread needs to wait here for some other thread. And this is basically something which can be implemented just with semaphore or with any other locking primitive. And when should we use that? Well, depending on how it's implemented internally. If it's implemented in a way which gives us performance benefits in our case, then we should use it. Otherwise, we can just go with any mutex or lock or whatever else. But if we are talking about the barrier, like read barrier or write barrier in garbage collector, then it's something completely different and we should not be using it. We won't be discussing it in this talk. Okay, moving on. So we do have sleep and spin wait, and there's one more typical concurrency primitive which we would like to use, which is a pattern when we are waiting for some condition to happen. So we have an infinite loop on the left side, which is trying to lock on the sync variable, which is whatever it can be, and then we check the condition. If the condition meets, then we do some work. Otherwise, we can't proceed because the condition is not met. So we should wait for the condition to happen. However, we need to loop again, release the lock because probably something else is changing this condition inside the lock as well. So we need to release the lock and then acquire it again when the condition is met. So how do we do that? Well, mutual exclusion here is not enough, because if it, like, we have this question whether we should sleep in this else branch, or maybe we should hog the CPU and do the spin wait, or what should we do? And the answer to that is there is a monitor thing. So this is a concurrency primitive, which is used exactly to do things like that. So instead of just looping forever and taking a lock, we should use a monitor, which is a mechanism which allows us to go to sleep and be notified not only when the monitor is can be acquired again, but also that the condition is met. And in that case, we'll not only be like woken up, but we'll also acquire the monitor immediately. And this is the construct we should be using in such a scenario. However, the super important part of that is that we need to use it properly. So first, there is some Win API, pthreads, and .NET things which can be used. And in .NET specifically, we are using monitor pulse plus monitor wait. And the important thing is that we can be woken up in a so-called spurious manner, meaning that if we are trying to get the lock and then do monitor wait, so we go to sleep in this line of code, and then someone wakes us up, it does not necessarily mean that the condition is already met. It may be that we were woken up because of the device driver, because of someone called monitor pulse all, which wakes up everyone, or because of any other APC procedure or something else. So generally what we need to do is we need to take this lock and spin in a loop. Instead of if, we should have a while here to sleep as long as the condition is truly met. Now, when it comes to some taxonomy of locks, whether they are local, global, or what the differences are, generally, local locks are locks which are held within one process only. So we are talking about inter-thread locks when those threads are running within one application. And those locks can be implemented like in user space entirely. They do not need to be implemented in the kernel mode because, well, the user space can be used and all the threads have an access to the same memory. However, when we want to synchronize something between threads of different processes, then we need to use the global locks, and they need support from the operating system. They need to be named typically, so we can identify those locks from between threads. And because of that, because they are named, because they are implemented in the kernel, they are typically slower due to the kernel switching. However, locking between threads or between applications is not always enough. We need to have truly global locks. So locks which are held like between machines, between nodes. And they are typically implemented with a timeout because they are not locks. They are leases. So we only use some resource like a global database, global file, or whatever else. We'll get to examples of that a little later. And we do not take them like a lock which holds forever. We take them as a lease, meaning that we lock them only for some time, and we need to refresh this lease periodically. Otherwise, this locking mechanism assumes that we died. We cannot detect that something died on some different machine because we may have no network connectivity to that machine. We may lose access. That machine may be responding slowly. There are multiple cases in which we just can't communicate, and we cannot detect that the owner of the lock actually died or whether it's still running. So in all these cases, what we need to do is we need to take locks with a timeout. And this is actually a super important principle we should be applying in our regular inter-process communication or even in locking within one process. Never take locks without a timeout. Always take locks with timeouts, because odds are that you will hit this timeout anyway sooner or later. There may be bug, there may be invalid memory access, something you don't predict, you do not foresee, which will actually crash the thread owning the lock. And if you wait for the mutex to be acquired without the timeout, you will have a deadlock effectively. So now, what are the issues with locks? Well, first question we already asked, what if a thread dies? What if it died in the middle of critical section? First, do we get a notification that the thread died in the middle? If we do not get the notification, then we don't even know it's dead. So we will just be waiting forever, right? We'll wait for it to finish, it's dead, so it will never finish. So effectively our application stops and is deadlocked. But if we do get the notification, can we safely carry on? Can we continue? Is the data in consistent state or not? Should it be rolled back? Should we kill the process? Should we start the process from scratch, or can we just safely move on? What if we are using a semaphore? Like, how do we reset the counter? By how much? How do we get the notification? What if that was an inter-machine log? So log like in between machines. How do we detect that something died on the other end? We want to have a timeout which is long enough for the process like to finish the operation it needs to do in the critical section, even taking into account like hogging the CPU or lower resources or some issues on the network. On the other hand, when the thread dies or where the process dies, we want to be notified about that as soon as possible. Maybe we should implement some pinging, some watchdog, some other communication mechanism. But if we do implement a ping, it probably runs on a different thread. What if that other thread is the only thread alive? Like the ping mechanism works, but the thread actually owning the log died. How do we implement that? And it's not trivial. There are generally multiple things we need to consider here, and this is non-trivial to implement like reliably. What about priority inversion? Let's say that our thread wants to get a lock, which is now currently being held by some other thread, which is running on a much lower priority. Right? So we are like a critical thread, and that other thread has priority set to idle or low priority. But if it has such a low priority, then it will get CPU much less often. So because we are waiting for it, like we'll wait for way longer than we want to wait because we are a critical thread. So we get a priority inversion. That idle thread now needs to get its priority bumped up so it can continue and finish the critical section much faster so the critical thread can carry on. And there are other questions. How can we see who holds the lock? Is it possible at all? Does the Win API or any other API you use allow you or give you the insight who owns the lock and what the thread it is, right? Or how can we take the thread, take the lock forcefully? How can we evict the current lock owner so we basically take over the lock? And again, always acquire a lock with a timeout. Never do that without a timeout because sooner or later you just hit a deadlock. And this is something which we may seem very unlikely or may happen very rarely, but generally always put a timeout no matter how crazy it is. If your operation finishes like in 1 second, then put a timeout of 1 hour. This timeout will probably never be hit if your application is correct, but one day you may be surprised, oh, this deadlock, this timeout was actually hit. What happened? Now, coming to some real-life scenarios. So the first scenario I'm going to show you where locking may be tricky is actually a place where there are no locks. We are talking about .NET here, and we are talking about finalizers. So when you are exiting the application, a finalizer may be executed. So you have some object which implements IDisposable, and you are now exiting. Your application tries to exit, and what you have now, your finalizer should be executed, should in turn call the dispose method and clean this resource up. However, this is unreliable, and once I hit a very interesting bug in the .NET application which was related to finalizers. So what I had is I had a very simple application which was just writing something to the file. Let's make this a little bigger. So we have a method which basically writes to file. So it takes a stream of whatever, and writes JSON, any data to the file, okay? And it's using the using keyword because this object, this stream and this writer, they are disposable. Now, what happens if some other thread wants to terminate the application by calling environment exit or whatever when you are inside this write operation? And there is a bug. I mean, definitely there was a bug in .NET, and I could reproduce it even in .NET Core, so probably the bug is still there, which resulted in a double access to this method. So this method being executed twice. Why? Because when you call environment exit, your finalizers may be called by your .NET application, by your .NET runtime. So your main thread executing this line may actually be done with writing, and then some other thread may start calling the finalizer of the file stream, which may result in flashing the stream again. So let's see what we are trying to do. This is a very simple application which has like a main method which goes simple, which runs in two modes. Either we are the main mode, and the main mode is basically writing to file, spinning to threads. One thread tries to write to the file, the other thread tries to call environment exit, so exit the process. And the other mode of this application is we just run this in the loop, and we run it as long as we try writing ABC to the file and we get duplicate content, okay? So you can see that currently the file we are writing to has content of ABC, so it has been written properly. Now, I won't be running this because I'm sharing my screen, but I do have a video here, which I can now play. Hopefully you can see this video, and you can see that this application is being constantly triggered, and it seems to work correctly until at some point we'll detect that actually the content of the file was completely different, was broken. Why? Because when running environment exit, the finalizer was executed in a parallel way, like by two different threads, and which resulted in flashing the stream twice. So you can see that it happened, and you can see that now the file which we just seen, which had content of ABC, has the content of ABC. And this is an issue which you can get with your .NET application if you are trying to write a file. How can we fix that? Well, the answer, the solution in my case was calling GC suppress finalize. So the finalizer was not called neither on stream nor on writer, because I was calling those dispose methods manually. And this is something probably you can hit very rarely. In my case, I was hitting this situation once every like 3 to 4 months. And finally, I decided to debug it, and this is what I found. So this is one of the issues you may get with locking. The other issue with locking is the commonly wrong pattern. The pattern you can see in the documentation, which was actually buggy in .NET, which is buggy in multiple other platforms, and you cannot take it for granted. So the pattern looks like this. Whenever you try to take some locking, and there is a question in the chat, have you created an issue for this? No, I have not created an issue for this, for the finalizer, assuming that's what we are talking about, because this is as expected. This is an expected behavior. Your finalizer is not guaranteed to run, but is allowed to run, and the locking should be done on your way, on your side, because it should be you who guarantees that those methods like flash method, which is not thread safe, it's not marked as thread safe, that you synchronize on that method. So you should make sure that you take locks on your end. In my case, GC suppress finalize was the solution. So there is not a bug per se, like the .NET platform is buggy. However, there is this type of behavior which we may not be aware of, which may result in bug or buggy concurrent access. And it's very hard to spot because it's super rare. Anyway, coming back to the pattern. So typically documentation tells you that, hey, if you want to lock something and you want to use try finally, you first acquire the lock, then you enter the try block, and in finally, you just release the lock. Okay, so if you did not acquire the lock, then probably some exception was thrown or whatever, or you never entered try. So you do not call the release lock in finally because you're not in the try block yet. However, the problem is that there may be something wrong in between you end acquire lock method and before you enter the try block. And this is something like very crazy situation. Someone kills the thread, you get some wrong out of memory, you get some completely crazy invalid memory access, something hijacked your thread to run an APC and it crashed or whatever else. And this may result in the lock being taken forever, acquired forever, because there is no, like the thread dies before entering the try block, so it never releases the lock. Even .NET had this issue, and this is an actual issue from .NET. Just like when we are using the, do we have it here? No, let's open the Visual Studio. Do I have any locking here? Or maybe I don't. Well, probably I don't. Anyway, when we are using the lock keyword in .NET, what it's doing under the hood, it's compiled to the operation monitor enter, and then finally we have monitor exit. And there was a bug in .NET platform that monitor enter, or actually the just-in-time compiler was introducing a NOP operation after monitor enter finished and before entering the try block. And this NOP operation was added just to make the code aligned on like 64-bit boundary, so it's better to use on 64-bit machines. However, the issue was that when we are executing this NOP instruction, then something wrong could happen. Microsoft reworked that, so now the monitor enter is executed inside the try block, and it atomically also sets a flag indicating whether the lock was taken or not. However, this pattern is so common in multiple applications, multiple languages, multiple documentations, that it's like, it's very common. But those applications, those platforms do not give you any guarantee that nothing wrong will happen between acquire lock and the try block. Same issue is actually, or similar issue is actually with this, the very popular pattern called double checked lock. Like you are checking, if you want to initialize a resource, you check whether the resource is null. If it is, then you take the lock, check the resource whether it's null again. That's why it's called double checked lock, and only then you initialize the resource. And the reason for that, why we use double checked lock, is that this first if, which is outside of the lock, is to increase the performance, to make the code running faster. However, it is also a wrong pattern. Why? Because due to memory optimizations and memory model, we are comparing a variable which is modified on some other thread. Then your compiler may decide, okay, this will never change. This memory will always be null. So feel free to take a look at that and don't use double check lock, and don't use this pattern if possible, because they may just cause you a headache. Now, coming to some other locks we may hit like accidentally without realizing. There is a heap lock in Windows, and generally when you allocate some memory with malloc or with any other like memory library, there is typically a lock being taken because you need to modify some structures describing you the heap. Okay, because you allocate some new memory page or whatever, you bump the pointer, so we just lock this thingy. And now if you are allocating the memory with like seemingly completely okay called new object, and something kills your thread in the middle or pauses the thread in the middle for whatever reason, it may be that you are actually now holding a lock to the heap and your whole application deadlocks forever, because other threads will probably try to get this lock as well, and you hold it, you died, lock is taken, and you don't know whether the heap is consistent or whatever else. So generally, never kill your threads, never pause them, because they may be holding such an innocent lock just with the new object. And obviously, memory allocation is pretty common. That's why .NET also introduced the thing which is called critical region. And in critical region, you are not allowed to allocate any memory, just to avoid situation with locks for the heap. Another lock on Windows platform is DLL main lock. So when a new module is loaded into the process, which may happen anytime because you are just using some new C# class, which was not yet loaded into the memory, okay? So the new module must be loaded. And if that module executes some like DLL main function, which is an entry point of the module, and tries to load some other module as well, then because you are currently loading a module, you are holding a lock for modifying the structures of the process, you get a deadlock again. This is a pretty common source of deadlocking issues on Windows. So if you ever run something in the entry point of your module, something which is not directly exposed in C# in .NET assemblies, but generally is allowed, is exposed easily in C++, then be careful when you are doing operations in the DLL main, because, well, you hit another deadlock. Yet another situation is related to the mechanism in Windows called APC, asynchronous procedure call. That's a mechanism to deliver a message to the thread. So this is a mechanism which can be used, for instance, to deliver a message from the driver that, hey, the memory or the network packet already arrived and you can use it. This APC can be executed on top of your thread, meaning that your thread, which is executing your business logic, is paused by the operating system and then is locked because it needs to use some other message from APC. And actually, if you go to like MSDN and Windows documentation, you can find tons of different locking primitives which can be used in such a scenario, right? Windows gives you multiple different ways of locking the memory, depending what you need to do, what guarantees you would like to have, what fairness you want to support. So it's not only about like different one single lock, but also depending on what you're trying to do. Now, talking about Windows and drivers. Windows never wants to risk breaking a physical device. So if there is a buggy driver and you want to cancel some IO operation, you probably have seen that you want to, I don't know, access a network share, and there is this dialog with like a progress bar, and you are fed up with waiting for it for 5 minutes, so you want to cancel it. You click cancel, and then you wait another 5 minutes because nothing happens. Why is that? Because Windows never wants to stop a driver if it's not sure, not convinced that the driver finished all its operations. So it won't kill the driver what allowed if the driver does not respond. So in those situations, when your driver is basically unresponsive, Windows will not try stopping it, will not try killing it, will not try unloading it. In these scenarios, you effectively risk some deadlock and you may be forced to restart your operating system because that's the only way of like releasing the driver or releasing device altogether. So those are situations in which like you can't do something because Windows stops you. And this can affect your applications because imagine that you are reading some file from like a network share or from a drive which is accessed by the driver and the driver got stuck. Windows will not let you kill the application which is trying to access that data. Otherwise, it would risk the corruption because the driver is running on the thread from your application. So effectively, those are situations when we may be stopped from like continuing because, hey, something very bad happened. And moving on even down the line to the kernel mode locks, there is a concept of interruptions, which I already mentioned, and there is a concept of interruption levels. And interruption level, like IRQ level, is a level telling you what you can do when it comes to the deep internal CPU structures. Some of those levels are used to support things like memory management. Some of those levels are even used to synchronize things between CPUs. So there is an IRQL level which allows you to basically stop all the threads of your CPU and run only one of them to modify some structures. So this is IRQL level, and there are obviously other mechanisms for locking between those things. There are also cloud leases. So locks which you can use to access some Azure Blob or Zookeeper logs or some other things which you can need to synchronize in between applications, between nodes, between machines. And they operate on the same idea like network timeout. So you basically go to some resource, you ask it, hey, I'd like to acquire you for 1 minute, and I'll be refreshing you every 10 seconds. If I stop doing that for a minute, then you assume I died. So that's the idea for cloud leases. And actually, you should consider all your logs to be leases, not locks, and like always await with timeout. Other ideas, well, Microsoft SQL Server gives you 2 different types of locking primitives. One of them being locks you can use in your transaction management. So you have transaction consistency, so you have like serializable level isolation, or maybe read committed. But the other primitive is for latching. So those are locks which are used by the SQL server itself to protect its own internal heaps, pages, B trees, whatever else. And ultimately, there is the last type of locks which we use, and this is a logical transaction lock. Imagine that you are buying a ticket to some event and you want to choose a seating, which place you'd like to sit at. And the system probably works in a way that it allows you to confirm the transaction, or it requires you to confirm the transaction in like 15 minutes, or generally some time. Otherwise, you lose your seating if you don't pay for the ticket, right? This is again based on timeouts, and this is something which you are not considering like being locking primitives per se, because this is more of a business decision in that situation. And now going to the algorithms and then seeing actual implementation. When it comes to algorithm, Decker's algorithm is the first known algorithm to implement locking. The way it works is, and this is obviously a pseudocode, is we have 2 threads only, we cannot have more than that, and we have 2 flags, and we do not use any memory caching in between. What we do is we need to have all the memory barriers or the code reordering on the CPU management disabled for that, because otherwise this algorithm would break. So you cannot implement this algorithm directly nowadays. You could implement it directly on your CPU like 40 or 50 years ago. The way it works is we just loop indefinitely. We check the flag of the other thread. This works. The problem is it doesn't scale to multiple threads. Peterson's algorithm solves that. So it works for n processes, and this is how we can implement the locking in multiple threads. Obviously, there are different algorithms like Szymański's, Lambort's, etc. They support give you different properties. For instance, fairness, or the order of who takes the lock in case it's contended, and other stuff. But we won't be getting into those details. But the important thing about locking is, if we do use locks, how can we reason about that? Like, can we build some mathematical model to understand how those locks operate and how we can reason whether our algorithm is correct or not? And the answer is yes, we do have multiple mathematical models. The most common nowadays is the temporal logic of actions called TLA+. So TLA+, you do have an example of that on the right side of the screen. Is basically like a mathematical language, mathematical representation of the operations you execute, and it allows you to basically prove that your multi-threading algorithm is correct. It will not deadlock, it will finish in finite steps, it will do what you think it's doing. You can prove it. Just like with calc, you can prove other properties of your application. TLA Plus allows you to reason about concurrency. However, there are different other models which are greatly explored. For instance, communicating sequential process, CSP, or the actor model, which is pretty popular nowadays. Those things allow you to structure the concurrency in a different way to reason about it easier. But the thing we need to remember is there are caches and memory models. So we do not read, whenever we run the application, it doesn't go to the RAM memory directly anymore. It always goes through the CPU caches like level 1, 2, or 3 to get the data. So whenever we read something from RAM, it needs to go through caches. And now, level 1 and level 2 of caches are per CPU, meaning that when you are trying to read something from RAM, then effectively you are reading it from your cache, which is exclusive to your CPU core. Other CPU cores have their own caches, meaning that once you read some value, you never operate on this value in the RAM memory directly anymore. CPU takes care of that. And in order to support that, we need to have a protocol called MESI, Illinois, which gives us 4 different states. And this gives us one important problem, which is called false sharing. The false sharing problem is when we are reading memory, which is cached into the memory lines where each memory line is 64 bytes long, when we are trying to access that memory, we may be inadvertently caching or competing with some other CPU. If we take a look at situation here, we do have an array of like 17 elements. Each integer is 4 bytes long, so we have 68 bytes here, okay? And if we now run two different threads, when first thread runs on the or modifies the element number 0, and the second thread modifies the element number 1, even though those are two completely different elements in this array, they still fall into the same memory line. The same memory line, which is 64 bytes long on like today's CPUs, which means that this operation will need to constantly flush its cache and resynchronize it with the cache of the other CPU. This is called false sharing. It's false sharing because we do not share anything explicitly, but we share it on the CPU level. And if we run this thing with indexes 0 and 1, so accessing elements 0 and 1 from this array, this application will perform way slower than if we change this one to 16. Because in that case, we would have two threads accessing two different cache memory lines, which would be way faster. And when it comes to similar situation, we probably have seen this issue with drivers, with IRQL, with blue screen of death, which sometimes mentions that, hey, something was IRQL not less or equal here at the bottom level. What it tells us is the operating system, the driver, was trying to get some lock when it was not supposed to or was not allowed to do that. For instance, it tried sleeping when it was not possible. So those are issues with these algorithms, but on the bright side, there are multiple different collections or structures we can use to avoid the locking primitives altogether. For instance, there is a blocking collection in .NET, there is obviously a task run, executor in service in Java, and other primitives for like completable futures. Generally, we should avoid building those things by hand because there are multiple issues with them. And if we want to look for some other solutions as well, obviously there are different platforms, frameworks, actors approach, agents approach, or even COM solutions, which we probably don't use nowadays. But ultimately, whenever we try dealing with locks, we should always go for lock-free programming, meaning that if we are trying to do something multi-threaded, we should not be using locks at all. Instead, we should be using code which uses the compare and swap operation, which is like lock-free, and in which case we do not wait for the critical section to complete, so we don't block the thread. There are multiple ways, multiple types of lock-free programming, and they pose multiple different issues. For instance, ABA problem, or we need to deal with memory reordering or starvation, but generally this is an approach which allows us to, or gives us the best performance if we need to have it. And since we are talking about .NET from time to time, we need to also ask the question, what about async? What problems do we have with async programming when it comes to locking? So async is not about concurrency nor parallelism. It's about unblocking the thread. However, the important part about async is that it's not tied to a thread, meaning that whenever we await something just like here, we don't know whether this continuation is going to be executed on the same thread or on a different one. So that's why if we try compiling this code in C#, this lock will, like this code will not compile at all. .NET compiler will stop us from running await code inside a lock statement because, well, it cannot be used here. Why? Because if it happens that we take a monitor here, so we take a lock on this thread, and then this continuation happens to run on some different thread, then effectively first, we are not running inside a lock anymore. And second, we'll get an exception that we tried releasing a lock which we didn't own. However, nothing stops us from implementing this code by hand. And this is the example of what I'm talking about. If we change the lock construct into monitor enter, just like it's compiled by the C# compiler, then this code obviously compiles and seems to be working. However, this is the exception we get. Like object synchronization method was called from an unsynchronized block of code, meaning that this monitor exit was executed on a different thread, on a thread number 4, whereas it was thread number 1 who took the lock here. So generally, we cannot use any locking primitives if we are doing an asynchronous programming in C#. How can we deal with that? Well, what we can do is we can use things like async lock, and you can find multiple implementations of an async lock out there on the internet, and you can at the same time find like articles telling you that reentrant recursive async lock is not possible. They are mostly wrong because technically it is possible to implement such a lock and it works. However, it is typically very hard to reason about that because we are not used to this concept of threads that the continuation runs on a different thread, especially that we have no guarantee where it runs. If we are running a code like this, await operation with configure await false, it seems to us that, hey, the continuation of this should be running on a different thread. But it's not always the case, because if the operation finishes synchronously, then we continue on the same thread. So reasoning about async code in terms of locking is way harder, but still, if we need to lock something in an async code, we do have like async lock primitives for that. And now getting down to some custom implementations. How can we implement a lock? So the first idea about semaphore, how we can implement a semaphore is like, why do we even need to implement semaphore with mutexes? I told you that semaphore does not have this notion of an owner. So it doesn't know who took it, who owns it, who acquired it. But sometimes we would like to basically get a semaphore, something which can let multiple threads enter the critical section, but still we would like to get all the benefits of the mutexes, meaning that if a thread dies, then we get a notification, we know which thread died, etc. And the approach we can take is, instead of using one semaphore, we can take an array of mutexes. And what we do is we wait any of those mutexes, and if any of those mutexes was acquired, then we basically get the ID of the acquired mutex, and we can safely carry on. And we know which mutex to take and which mutex to release. So this is first way of implementing something like semaphores with mutexes. But carrying on, imagine that we don't have mutexes, do not have semaphores. We can use a file to implement a lock. If we are not going to implement something directly, we can just use some other primitives and build this file locking structure. What do we do? Like in .NET, we can just create a file stream and indicate that we do not want to share this file with anyone. In that case, when some other thread tries to access this file, open it, write to it, or read from it, it will be just blocked by the operating system because this lock is being taken already. This can be useful if we are, for instance, trying to implement like inter-process lock when processes are running on different operating systems or different machines, because we can use a network file storage to implement such a lock. Obviously, not all NFS file systems support that, but generally most of them do. And in that case, we can just implement a very simple inter-machine lock just with files. And now comes some other question, like mutex with ownership tracking. And this is yet another issue which I hit at some point, that Windows mutex doesn't tell you who owns it. If you take a mutex like a inter-process mutex in Windows, it doesn't let you check who is the owner. And it happens that if the owner dies for whatever reason, and worse, if the owner is still alive, but it's holding the mutex for way too long, for instance, it's holding it for an hour instead of like a second, we have no idea of who the owner is and how to kill it, how to stop it, how to get or reacquire this mutex. And now comes the question, how how can we implement such a mutex which gives us the ownership tracking and still works in between between processes and between threads? And the idea is we create a memory mapped file which anyone can view. So any process and the computer can map this memory into its memory space and access the same shared memory. And then we will use compare and swap operation to store 64 bits of data inside this memory mapped file. 32 bits for the process ID and 32 bits for the thread ID. So we basically store the owner inside that shared memory. And then when compare and swap fails, that we know someone holds the mutex, we can kill it, we can debug it, we can do whatever magic. So let's see a source code for that. So what we are doing is we do need to in .NET import like interlocked compare exchange, so compare and swap operation. We need to also import a couple other operations which will be used for the memory mapping. And the first thing, if we are trying to do something with mutex, so we get like the name of the mutex, we get the lambda which will allow us to the operation which we want to execute while holding the mutex, and a couple other things. And what we do is we store the process ID and thread ID inside one long field. We get the timeout for how long we would like to hold this mutex, and then we carry on. We create the memory mapped file. We get the stream of that, and now comes the thing which we are trying to do with the very unsafe operation. So we get a pointer to the actual memory, which is there, which is mapped to our process now, and we execute the interlocked compare exchange operation. So we execute the compare and swap operation, and what we are doing is we try to replace the memory backed by this pointer with my identifier if it was 0. So if the memory there was 0, then we replace it with our identifier of our owner. And if it was 0, then we can execute the action, and then we can return, and there is a finally block which releases the lock. However, otherwise, we get the previous holder basically from this memory here, from this compare and swap operation. And now we can check whether this owner was running for long enough, like 1 hour. We get the process ID. We can check whether the thread is still alive. If it was still alive, then we can try clearing the lock. We can then do some other things. For instance, we can try killing the process, and also we can try running CDB to take the memory dump and do some other things. So this is the general concept of how we can implement such a lock. And I'm running this or using this lock actually in production for, I think, 5 years now. Seems to be working correctly. Obviously, I haven't checked it with all the mathematical models which are out there available. However, this seems to be working well now. There's a question actually. Are you sure that your action lambda will not leak in unsafe code section? I'm not sure what do you mean leak in this context, but generally I don't see how it should leak. I mean, this action, if it breaks, then there is obviously using, which will clear the memory, and there is try with finally at the very end, which will try clearing the lock. So this should work well. If there is some other issue, well, I haven't spotted it yet for like 5 years. So seems to be, I'd say, pretty stable. However, this implementation seems to be simple, like the idea is super simple, but still it took like something like 200 lines of code just to implement this thingy. And it has multiple other issues with that. First, it's not fair at all, meaning that if there is a lock contention, so there are multiple threads trying to acquire this lock, then like there is a race and there is no clear winner. It may be that the thread who comes first may not actually be like the thread who will own the lock after it's released. And this may lead to like a killing storm, because we are trying to kill the owner. We need to make sure that we are not like killing the owners like crazy because we are waiting for too long. Also, Also, I'm trying to take a memory dump in this log. You can see here that I'm running a CDB, so the debugger, to take a memory dump of the application. And this is also risky, because if you try debugging your application with CDB, it may happen that taking a memory dump fails, and then the process becomes a zombie, and you cannot kill it, and it doesn't work, and you cannot even detach the debugger from it. So you are basically like doomed in that case. So taking a memory dump of something may also be a source of multiple problems. Also, there is a spin weight in this log, obviously, so it hogs the CPU. And yet another thingy is I'm storing 32-bit identifiers of the process and of the thread, meaning that if something like the identifier can be reused, ideally, I should be using 64-bit identifiers in that case, so supporting 128 bits of data. But the problem with this approach is this is not something we can do with compare and swap on all the CPUs, because your CPU may just not support such a compare and swap. And also, it doesn't support reentrancy. Right? So if you take the lock, you cannot take it recursively, because when leaving, you just clean the lock. You would need to hold yet another counter correlated with it, so that would increase the complexity of the lock, and it's just the beginning. Implementing a lock is not a trivial thingy, even in such a trivial scenario. Summary: avoid locks when possible. Just use some different structures or different like consumer producer collections, or something which is implemented, well tested, battle tested, and works well, even though there are bugs in situations like this. Like a friend of mine found bug in concurrent dictionary in JVM, like Java 9 or 10 it was. So generally those things can be buggy, but avoid writing your own. Keep your critical sections as short as possible, and always take logs with timeouts. Otherwise, you may hit deadlocks or timeouts, which are super unexpected, and sooner or later you will hit them, especially if you are dealing with like pinvoke and interrupts and other things which increase the risk that your application breaks in an unexpected way. Always take a timeout, as I mentioned. Don't use lock in async. Avoid locking in async at all, because even async lock mechanisms, they are available out there, but they may not work reliably for you, and it's much harder to reason about that. And being that said, I guess that's it. If you do have any questions, now it's a great time to ask them. And right after the Q&A, we'll just carry on with some references.
And guys, if you don't want to type your question, you can push raise hand button and I will unmute you.
Okay. In the meantime, I do see a couple of questions. Question number 1, could you please share best practices, advice, resources for looking when two processes use shared memory? I do not have anything addressing directly that, like processes using shared memory. Probably you could read Concurrent Programming on Windows by Joe Duffy. Or actually, let's go to references. Concurrent Programming on Windows is a very nice place to read about this typical scenarios about like concurrency in Windows, and it goes pretty low level. So maybe this will give you some idea. It also covers a very nice part of why .NET on Windows does not support fibers or does not support green threads in general. It's not that it's not supporting them, it's explicitly unsupporting them. This also like gives you a great understanding why async looks the way it does in C#, which may not be the best solution. Anyway, concurrent programming on Windows. Then the art of multiprocessor programming. This is actually a great book if you'd like to learn about how to implement locks which are fast, reliable, and use lock-free code if possible. So generally a way to go. Also, Pro.NET Performance or Patterns of Parallel Programming, they are pretty nice reads if you are not interested in like that crazy low-level details. So yeah, I think this is the place where to go. When it comes to other things, and also including the lock I showed you, it's on my blog. So there is a series about concurrency on my blog, and there is also a series about async wandering, where I show just those things, and a couple other links for you if you'd like to read about those different concepts. Coming back to the Q&A then. So the question 1, I think we covered. Question 2, could you please share some most common cases when we use, as usual, use locks, but we can implement it without locks? So the situations where we do use locks, but we would like to go without them, and common situations for that. For instance, double-checked lock is something which we typically use locking, but we probably could get rid of it if the resource allocation is cheap. Other situations when we don't need to use locking, actually, whenever you want to implement like a producer consumer, you should be using a structure for that, not implement something like, you know, concurrent bug or concurrent list and use it like from multiple threads. That is because those producers to consumers can be extremely optimized. Like they obviously need to do some sort of locking under the hood, but for instance, those locks can be optimized to not lock the whole data structure, but only like a very little part of the memory, like a memory page or even smaller. In that case, you are effectively going with no locks if you, depending on the load and on the usage. So generally there is, like, I can't give you a single place that, hey, you do this with lock, go without that. But generally there are places in which just replacing one locking structure with the other one may actually effectively give you a code which doesn't use locks anymore. And the question number 3, interlocks too in .NET, are they more safe locks tools for some scenarios? Again, depends on the use case. The Art of Multiprocessor Programming book like explains that in a fantastic way, showing you where you can go without locks and go with compare and swap operations, especially if you are dealing with like functional programming, for instance. All the immutable data structures, when you are trying to modify them, obviously by replacing part of it, can go with some optimized locking. So that's why sometimes, and is used like a lot in either functional programming or, for instance, in Scala language, not necessarily in functional parts, but with the immutable collections. Like instead of using like plain lists, you are building a tree, which is highly optimized because it locks only a particular level of the tree or particular branch of the tree, and even improves on the time complexity, like on a maths level. So generally, those are situations which are worth reading. Also, I think they are called CRDTs, curiously recurring data types or something like this. So types which enable you to perform concurrent operations without any locking, and those operations are can be executed multiple times without breaking the result. So they keep track of basically some messages which come to your system, and then recalculate the things in an out of order manner, so it doesn't matter what the order of messaging was. This gives you the correctness. That's the first thing. And second thing is they give you the better locking. So generally those are scenarios in which I would look for the answers, and probably there are many more. Moving on with questions, do you have samples on GitHub? Not on GitHub, it's on my blog, so the links should be there. Another question, how we should calculate how much time do we need to process a critical section? Should we always consider destination hardware? If so, do you know easy way to do that? That's generally a question which touches on the benchmarks and on the measuring the performance of your code at all. How should we calculate the time? Well, you can calculate it on a theoretical level. So basically, if you know what hardware you use, you can calculate how fast a memory access should be, and you can calculate how long the code should be executing for. That's like general approach, not something related to locking per se. Do you know an easy way to do so? There is not an easy way to do that. That is because, well, even measuring the code is super tricky. You can go in .NET, probably the easiest way is like using benchmark.NET library, which has pretty decent way of measuring the operations or calculating how long they take. However, like you need to take multiple aspects into the account, like caching on the CPU level, memory reordering, type of the CPU, whether operations are emulated or not, whether they are executed out of order or not, whether you have even the memory structure, whether you're running in NUMA mode, so non-uniform memory access or something else. So generally, you can't do that without understanding of the hardware you're running on. And there is not a simple way for doing that if you want to be precise. If you don't want to be precise, or whether some imprecision is acceptable, then probably benchmark.net should be just enough. Moving on, how do you debug and investigate deadlocks? Maybe some best practices. I do have a workshop on that for 2 days, taking 2 days in which I show different debugging scenarios. Some best practices. There is a great book called Advanced.NET Debugging by Mario Hewart. It shows you tons of useful information, shows you how to use WinDBG, memory dumps, how to get the logs and all that stuff. So I guess that's the best source for you if you'd like to learn that. Nothing else, like my recommendations probably won't beat what Mario described anyway. I don't, oh, there is a new message. Okay, one more question. Is it worth to change code to fit cache lines, play with object structures for common CRUD applications? Do you have experience with this? I'm not sure if I understand the question correctly. I think the way I understand it, should we like cut our structures in half so they fit into cache lines better? And when it comes to answering that, for CRUD applications, probably not worth it. Like you waste way more time in other parts of your app than just on memory lines. However, if you are doing like big data processing or if you are doing game dev, then the approach which is super popular there is data-driven design, which is DDD and coincides with domain-driven design, but is completely different. In data-driven design, we take this approach that we split the structures into arrays of properties. How does it work? If your user, like any entity, let's take entity called user, has like 4 different fields, like first name, last name, age, and I don't know, social security number, okay? And you hold, like in typical business application, you hold this structure as basically one structure with 4 different properties, okay? So now if you allocate 1,000 of those, you will have property 1, 2, 3, 4 of first instance, property 1, 2, 3, 4 of second instance, 1, 2, 3, 4 of third instance. Okay, this is how we would allocate that. And iterating over all those instances and modifying one property will be way slower because the caching line, well, will hold different data and you will need to load much more memory, etc. Data-driven design approach, which is pretty super popular in game dev, works on a different way. Instead of having one structure with 4 properties, you have 4 arrays. And the first array is the array of first names. And this array is basically first name of first instance, first name of second instance, and so on. And then you have another array for last names, another one for ages, another one for social security numbers. So now if your code wants to change like the first name of every single instance, what you do is you just iterate over that one array. And it fits in your cache line way better, is way faster, and allows you to operate on many more objects, like millions of instances, in a performant way. So this is the approach for business. Probably for CRUD applications, not worth it. But if you are dealing with like millions of instances and you need to transform them in a uniform way, then definitely worth taking a look. Another question, is it any specific unlocking in web apps cause of different synchronization contexts? I won't be touching on synchronization context here. There is another talk of mine, which is called Internals of Async, where I explain synchronization context in asynchronous programming. But generally, locking in web apps nowadays is no different than locking anywhere else. I'm not even sure if ASP.NET Core gives you or uses the synchronization context. It wasn't using it, and it was re-implemented to not use the synchronization context. So if you are not using Blazor, then you don't have sync context at all, and there should be much less locking, and definitely not something specifically crafted for the web applications per se. I guess that's it. I don't see any other questions. If you do happen to have any questions, post them in chat now, or feel free to speak up.